Welcome. Let's continue with the digestive system. Again, that's chapter 23 and 24 from your textbook and module 1. Today, we're going to be looking at the chemical digestion of particularly macronutrients. In the mouth, that starts with chemical digestion of carbohydrates and fats using enzymes such as amylase. Ase means that it's an enzyme. Lingual lipase. Lipase it has a prefix from lipids, and ase means it's an enzyme. So lingual means of the mouth. Lipase means fat, lipid, enzyme. Then in the stomach, we have enzymes like pepsin, another lingual ligase, and gastric lipase that are all functioning in the stomach. So these are digesting fats. Pepsin is digesting peptides or proteins. Then in the intestines, we have an intestinal amylase. We've got more lipases. We've got more peptidases such as trypsin. And then brush border enzymes such as sucrase, which digests sucrose or table sugar, lactase, which will digest lactose. This would be an enzyme that you might not have if you're lactose intolerant. Bile is released into the duodenum from the gallbladder and also from the pancreas. Bile is responsible for emulsifying fats. That's turning fats into these little balls, if you will, that can be absorbed into the lacteals. Bile salts are actually made from cholesterol. So one of the important functions of cholesterol is to help you absorb fat. So oftentimes when you hear people having high blood cholesterol, what that really means is they've got a high level of fat circulating in their bloodstream, and those fats are being measured by measuring the molecule that emulsifies those fats, which is cholesterol. So how do we absorb macronutrients? We break food down into monomers. So fats or triglycerides get broken down into their component fatty acids. Carbohydrates get broken down into monosaccharides, and protein gets broken down into amino acids. So if we look at the absorption of macromolecules, that only occurs after the breakdown. So simple sugars are absorbed into the blood, amino acids are absorbed into the blood, but fatty acids are absorbed into the lymphatic system via the lacteals. The blood, after it picks up the simple sugars and amino acids, passes by the liver, and the liver does a great job of monitoring the macronutrients as they're coming in, the breakdown products, the monomers from the macronutrients, and helps to regulate their dispersal to the rest of the body. On the other hand, fatty acids enter the lymphatic system, and the lymphatic system drops the fats into a subclavian vein that's underneath the clavicle, a vein just underneath the clavicle, and right here just above the heart. So you can imagine one of the consequences of a high-fat diet is in fact that the fats that you're consuming in your diet are being deposited directly next to your heart. The liver does make a very good effort at balancing nutrients. It absorbs some and releases others to smooth out the profile of, for example, amino acids in entering your blood. Hepatocytes will store away these nutrients, and sometimes they will add binding proteins to help their transport throughout the body. Hepatocytes also release bile into channels so that bile can enter the bile ducts. And here is a look at what happens with fats. So fats, when they enter the body, first of all, are found in these large lipid molecules called chylomicrons. Chylomicrons have apolipoproteins associated with them. They also have bile salts on the outsides, solubilizing them. And then they have a lot of fatty acids internally. Um, After the chylomicrons enter the system and are dropped into your blood, particularly under in your subclavian vein, the chylomicrons will circulate and reach the liver. When they reach the liver, they will get further postage stamps, if you will. Apolipoproteins will bind to these fat molecules and they become very low density lipoproteins. Very low density lipoproteins are sent around the body and the fats are absorbed from the very low density lipoprotein. So if you like, these are postage stamps saying, hey, deliver these fat particles to muscles, deliver these fat particles to adipose tissue, and then those fats are slowly delivered. As the fats are delivered, the particle size decreases to intermediate density lipoproteins and then low density lipoproteins. These are all forms of fat delivery trucks, if you will. Low density lipoproteins. The fats have been around the longest because these trucks have been delivering fats for the longest, and as a result, they tend to have the highest levels of oxidized fats. And oxidized fats can be pro-inflammatory and quite dangerous to the lining of your cardiovascular system, to the vasculature, the blood vessels lining your system. So you want to avoid having high levels of low density lipoproteins and very low density through low density lipoproteins. These are the at risk, these are the high risk um, lipoproteins in your blood. Now, after all the fats are delivered, you're going to with high density lipoproteins. These proteins have a important role. These particles have an important role. What they do is they return cholesterol back to the liver where it's recycled into bile salts, which can again absorb more fats. So these are the recycling trucks, if you will. They're recycling the cholesterol back to chylomicrons, and then chylomicrons are picking up more fats from your small intestine and delivering it to the body, processed in the liver, VLDLs, intermediate density lipoproteins, low density lipoproteins, the delivery trucks, and then finally the high density lipoproteins recycling trucks. Okay, this is a closer look at uh, chylomicrons, very low density lipoproteins, and low density lipoproteins. Chylomicrons are full of fat with some proteins associated with them. The very low density lipoproteins have these exchangeable apolipoproteins, as well as phospholipids, triglycerides, cholesterol, some free cholesterol, and some postage stamps. For example, apolipoprotein B100, which tells the fat globules where to be delivered, whether they're going to be delivered to um, your fatty tissues or to muscle cells and things like this. Low density lipoproteins have done some of the delivery already and are becoming more concentrated. And also, they've been around longer, so they tend to have more oxidized fats on the outside. And these low density lipoproteins are the ones that are probably the most dangerous in terms of cardiovascular disease risk in your blood. Okay, chylomicrons, large, very low density, transported easily around the body. The liver will process these into VLDLs, which are made in the liver. Their function is to deliver fats around the body. Low density lipoproteins are delivering fats to different cells. They become oxidized and can be quite pro-inflammatory and fairly dangerous. And then the empty low density lipoproteins become high density lipoproteins, and these are good, what sometimes called good cholesterol. These are returning the cholesterol from the cells after delivery and recycling cholesterol back to the liver where it will be turned back into bile salts. And these tend to have correlate with anti-inflammatory activities or correlate with health. So high density lipoproteins, in fact, having high levels of those is quite healthy. And this looks at that whole process. The intestines, fats are absorbed from the intestines into chylomicrons. The liver processes chylomicrons into very low density lipoproteins, which become low density lipoproteins, which deliver fats to cells. After those cells have delivered their low density lipoproteins, they become high density lipoproteins, which reverse the cholesterol transport, take cholesterol back to the liver, where it can be turned into bile salts. And the bile salts restart the process. Bile salts go into the intestines and help absorb fats and turn them into chylomicrons again, which starts this whole process once more. This is what a blood lipid test would look like for a healthy person. Um, you'll see things like total cholesterol. What this means, total cholesterol, means all of the cholesterols in the body. So that would be cholesterol found in chylomicrons, cholesterol found in very low density lipoproteins, cholesterol found in intermediate and low density lipoproteins, and cholesterol found in HDLs. Now, if this total cholesterol number is very high, your physician will look to see down here if the HDL, the recycling lipids, are also high. So these HDL, these are high density lipoproteins. These are your recycling ones. You would like this number to be high. In this case, they are above 40 milligrams per deciliter, so this is a good number. In this case, the total cholesterol is below 200 milligrams per deciliter, which means that this person is in a healthy range for their cholesterol. They also have high HDLs. So down at the bottom, you'll see a total cholesterol to HDL ratio. And this is probably the most important number for you or your physician to take a look at. When you can see this cholesterol to HDL ratio is less than 5, that means that the number of trucks delivering fats to the recycling trucks, the ratio of those trucks is good. The empty trucks is good. The full trucks to empty trucks is good. And when that ratio is below 5, that means that's a healthy ratio. And there's a little risk of the long-lived low-density lipoproteins causing damage to your cardiovascular system. And damage to your cardiovascular system looks like blockages in your blood vessels, and potentially heart attacks and strokes. You can see also this person has low-density lipoprotein, LDL cholesterol, which is the most dangerous cholesterol in the normal range. Here, theirs is 93, which is optimal, below 100 milligrams per deciliter. Anything less than 130 is considered okay, but in this case, this person has very healthy blood lipids. This is me. If LDL cholesterol is long-lived and there is a lot of LDL cholesterol, that the LDL cholesterol can become deposited on the walls of your arteries. And this happens at sites of inflammation. And when that happens, you can get these fat-filled deposits lining your blood vessels. And that would be like this here. And it often has a fibrous cap. That means fibroblasts are growing over the top of it, essentially like a scar, and it can become quite hard. If this peels off, it can block the blood vessel, and when that blood vessel is blocked, if that blood vessel is blocked and you can no longer deliver oxygen to your brain, that will cause a stroke. If this blood vessel becomes blocked because this plaque peels off and blocks delivery of oxygen to your heart, then that would cause a heart attack. Okay, next up, let's look at carbohydrate digestion. Carbohydrate digestion occurs mostly in the small intestine. Most carbohydrate is digested in the small intestine. Pancreatic amylase is secreted by the pancreas. It is a starch digesting enzyme. It breaks down starch into glucose, and that glucose is absorbed by your body. There are also specific enzymes that break down disaccharides. A disaccharide is two sugar molecules joined together, typically glucose and one other glucose monomer. Um, Maltase, for example, breaks down a glucose dimer. Sucrase breaks down a sucrose. um, which is a fructose, a glucose dimer, and lactase breaks down the dimer of glucose and galactose. This lactase will have low activity in individuals who are lactose intolerant. Fiber is also made of sugars. However, fibers have chemical bonds that we as humans lack the enzymes to break. However, um, microbes in your microbiome can break down some of these bonds and feed off fiber. So, fiber can start to feed the microbes in your microbiome because your microbiome have enzymes that can break down some of the fibers. And that can result in a significant source of energy, in fact. So some fibers can be digested partially to provide energy. But more than that, the fibers feed your microbiome, and your microbiome does a fantastic job of preventing infections, protecting you from infections, and making small molecules that talk to the rest of your body and keep you healthy. And this is a two-way street. By eating a high fiber diet, you keep your microbes happy, and by keeping your microbiome happy, your microbiome provides molecules to you, including some vitamins like vitamin K2 and certain B group vitamins. It can provide some of those to you, as well as producing small molecules like short chain fatty acids, which your body likes and benefits from. So, keeping a high fiber diet is a very healthy way to go. The uh, carbohydrate uptake in your intestines, and this is looking at cells of the intestines here, and you can imagine blood flowing here, and over on this side that there'd be sugars arriving for breakdown. For example, maltose broken down by amylase from starch will be broken into two glucoses and then transported across the cell into the blood. So glucose will enter the blood from starches. Fructose is transported directly via facilitated diffusion across cells of the intestines and directly into the blood. Glucose is absorbed, and this is quite interesting for those of you who like sports drinks like Gatorade. Glucose is absorbed in a co-transporter, and that co-transporter requires sodium or salt. So sodium and glucose are transported together into the blood. Um, and that's an important pathway. And galactose from that breakdown of glucose and galactose from lactose is transported across into the blood as well. Protein uptake is constant, and we need uh, continual supplies of protein. Um, those of you who work out regularly will know that if you work out hard, you get very sore muscles, and that's because of the damage that occurs to the muscles. It's some breakdown, and then your body will resynthesize muscle in a way that it's stronger the next workout. So to be able to do that resynthesis, we need to continually eat protein to provide the amino acids that are necessary for that new muscle protein synthesis. So amino acids are needed constantly for building and rebuilding muscle. If one does not eat enough glucose, does not eat enough carbohydrate, then protein will be broken down and stripped of nitrogen. And so that when that happens, basically in a situation where you're just not eating enough carbohydrate, and sometimes you hear people talking about low carbohydrate diets, and then they wonder why they can't put on muscle mass, and that's because your body will scavenge carbon and turn it into glucose because your body absolutely must have glucose. Your brain requires glucose. You've got to have glucose for muscle contraction. So glucose is essential. If you do not have enough glucose in your system, then muscle protein can be broken down and amino acids can be broken down and turned into glucose in a process called gluconeogenesis. So when amino acids are turned into glucose in the process called gluconeogenesis, which occurs primarily in the liver, the breakdown occurs in your muscles, but gluconeogenesis, turning those amino acids or turning your muscle essentially into glucose, that'll occur in your liver. But what the net result is if you have a very low carbohydrate diet, you can end up breaking down muscle mass and turning it into sugar. And so this is obviously counterproductive if you want to build muscle mass and build strength. You need to do so by having both carbohydrates and a constant supply of amino acids. Amino acids can also be turned into to hormones and certain neurotransmitters as well. To enable or to help your body digest protein, one method is cooking, because cooking denatures the proteins, which basically means unwinds the proteins and makes them more accessible to the peptidases, to the enzymes that break down proteins in your body. So, one of the ways that humans have adapted to make protein more easily available from our diet is cooking. And here you see somebody cooking an egg, and you can see how the egg goes from its non-denatured state here to its cooked state, where the proteins are denatured. So the proteins are here are tight and globular, and the proteins here are unwound and long, and they refract light differently. And so the egg becomes white, and the yellow becomes cooked as well. So this is the process of cooking. It denatures proteins, makes them easier to digest by opening them up for enzymes. Stomach acid has a similar does a similar thing. Hydrochloric acid also denatures proteins, essentially like cooking them, and it opens them up so they can be digested. Pepsinogen and pepsin are enzymes that chop up the denatured proteins. They do a much better job on denatured proteins than on proteins that are tight and globular and not denatured. So cooking or stomach acid both can help with the process of digesting protein. Hydrolysis reactions are reactions that are occurring in the small intestines, and pepsin and pepsinogen. They do these hydrolysis reactions, these peptidase enzymes break down peptides into amino acids. Those amino acids are taken up into the blood, and those amino acids are then used to synthesize new muscle, and indeed any other kind of structural material in your body that contains protein. Uh, when amino acids are digested, so amino acids enter the pool from the diet. So we eat protein, and the protein is broken down into amino acids. Those amino acids enter the amino acid pool. So one way of keeping this amino acid pool high is by eating protein throughout the day, and to have a fairly large pool of amino acids available. This is particularly important if you want to build body protein. In other words, if you want to synthesize more muscle mass. If you want to put on more muscle mass, eating a diet with a lot of protein in it can be very helpful. But you must also remember to eat a diet that's got sufficient carbohydrate. If it doesn't have carbohydrate, then you will break down body protein and proteolysis, and those amino acids will be turned into glucose. Now, if you eat too much protein, the protein can get catabolized, broken down, and it'll get broken down with byproducts, urea and carbon dioxide, and some other nitrogenous compounds can be synthesized from amino acids in the amino acid pool. But you'll notice that if you eat a high protein diet, you'll often end up with quite yellow, smelly urine because you're producing a lot of this byproduct, urea. And essentially, when you're pulling the nitrogen off there again, you're turning uh, amino acids into glucose. So one of the important things to learn in anatomy and physiology for what you see here is how food is regulated, food intakes are regulated. There are, as I've discussed a little bit before, there is nervous system stimulation directly from the stomach via the vagus nerve and also from the intestines via the vagus nerve all the way to the hypothalamus. Um, Talking to the satiety center to to tell your body that you are full and that you no longer need to eat. There are also hormones that talk from the stomach, from the intestines, back to your brain, and these control eating. There's many different kinds of hormones. For example, leptin. Um, Leptin is a peptide hormone that's released by fat tissues as they synthesize fatty acids and fill. And this talks to your brain to say, okay, that's enough fat. There are peptides like neuropeptide Y, NPY, which again talks to the hypothalamus and affects the feeding center. In that case, increases appetite. There are some other control mechanisms that I want to go into a little bit more detail on as well. So let's take a look at some of these mechanisms, hormones controlling food intake. At least in mice, one of the key mechanisms that hormones control food intake mice is through the hormone leptin. Leptin is released when there are lots of fats being stored in your fat cells, your adipocytes. Um, and if that hormone is not present, then the mouse will overeat and become obese. So this is a rat that contains a mutation, makes it unable to make the hormone leptin. So you can see where this might be important for human biology, given that there is a large percentage of Americans, around 30 to 35% of Americans, who currently suffer from obesity. Now, what we are seeing is a revolution in this field, um, in the sense that there are new drugs that are of the family of hormone agonists called GLP-1 agonists. And we're going to talk about those here in a second. But before we get there, we need to understand how blood sugar is regulated in the body. So when sugar is high in the body, the pancreas releases a hormone called insulin. Insulin helps us to regulate our blood sugar. So insulin is a good factor here. It's helping us regulate our blood sugar. Insulin has a number of effects. Insulin talks to our muscle cells and says, turn glucose, extra glucose in your blood into glycogen and store it. At the same time, it says turn amino acids into proteins. So insulin is a anabolic signal. That means that you build more muscle mass when you get a signal from insulin. And that's going to happen when you have glucose. So one of the things that you want to do after a workout is have some source of glucose to promote building muscle. But insulin also has some other effects. One of the other effects of insulin is it talks to fat tissue, adipose tissue, and says store more fat. And also to turn more amino acids into protein in fat tissues, which is basically grow more fat tissues. So this is not so good because now if you've got a high level of glucose all the time, you're starting to also store fat. You are producing muscle and you are producing fat. This works in tandem because as you put on weight and get heavier, you need more muscle to carry that extra weight. Now, insulin also affects the liver, where it tells the liver to store more glycogen and turn fatty acids into fats and turn amino acids into proteins in the liver. So these are all effects of insulin. So when you have a diet that's got a lot of glucose in it, or just after you've eaten a meal, glucose is high, and the pancreas will release insulin. As it releases insulin, glucose is stored, and and your blood glucose is kept in normal range, typically around 90 milligrams of glucose per 100 mils of blood. Now, when you're fasted in between meals, glucose levels can drop, and as they drop, as they drop, the pancreas will release an enzyme that counteracts insulin, works in the opposite direction. That hormone is called glucagon. Glucagon is a hormone that will tell the liver to break down glycogen and turn it into glucose. And again, that keeps your blood glucose in homeostasis. Now, there's yet another level of control beyond insulin and glucagon. Insulin for storing glucose, glucagon for releasing glucose. And that is where these new medications come into play. And then the hormone that regulates glucagon and insulin activity is a hormone called GLP-1. There's also another hormone called GIP. GIP and GLP-1 both work together in ways that regulate our blood sugar. But not only do they regulate our blood sugar, they also regulate through talking to the brain, they regulate our appetite. And they have a number of other functions as well. So GLP-1 enhances insulin activity, so makes insulin work better, which means you'll store more glucose, and at the same time, it inhibits glucagon activity, which prevents elevation of blood glucose by breaking down glycogen. So this is one of the functions of GLP-1, basically to regulate insulin and to regulate glucagon. So here we have a glucagon-like peptide 1, GLP-1. It's an 30 amino acid long peptide hormone derived specifically from proglucagon, which is the amino acid sequence that becomes glucagon. So as glucagon is made, your body also makes glucagon-like peptide 1, GLP-1. So your body makes glucagon, which acts in the opposite fashion of insulin, and GLP-1, which acts in combination to enhance insulin function. So your body is doing two things here at the same time. However, you can just give a patient GLP-1, and that's what these new medications are doing. The GLP-1 and GIP peptides are what are called incretins. That is, they have the ability to decrease blood sugar levels in a glucose-dependent manner by enhancing the actions and the secretion of insulin. So basically, GLP-1 is called insulinotropic. That means it acts the same or promotes the function of insulin. There are a number of GLP-1 related pharmaceuticals now that are available and becoming more and more popular. There's Ozempic, there's a once daily pill as well. Most of these are injectables. There's Wegovy, Trulicity, Byetta, Mounjaro. You'll probably see advertising for all of these because this is a multi-billion-dollar a year industry. Why is it a multi-billion-dollar a year industry? It's because around 1/3 of Americans suffer from obesity and need to reduce weight to improve their health. Is this the right way to do it? I'm going to talk to you about that right now and hopefully persuade you that no, this pharmaceutical is probably a poor choice for many people. It's certainly not a first choice. Diet and exercise will be your first choice, but failing diet and exercise, these GLP-1 related pharmaceuticals may be of use, particularly in people who are suffering from diabetes. So what do these GLP-1 agonists do? They function on the GLP-1 receptor. They have a number of important functions. Let's start with their most important functions. Their most important functions here are to talk to the brain. In the brain, GLP-1 agonists decrease appetite. They increase your feeling of fullness and they increase overall energy expenditure by your body. So, what does this mean in practical terms? In practical terms, what this means is people who take GLP-1 agonists, medications, typically start to feel nauseous when they see food. So your enjoyment of food plummets. And this can have some quite serious consequences. It can mean that people end up with inadequate diets without all the vitamins and minerals they need because they just simply do not eat enough food to provide their body with ingredients that they need, the essential vitamins and minerals that they need to be healthy. So this does have serious consequences, and many people who take GLP-1 agonists can end up in hospital if they are not careful with eating, and that is because they're put off eating dramatically. Food no longer has appeal to them. GLP-1 agonists decrease blood pressure, increase heart rate, increase the function of the heart, and are cardioprotective. So this is a good thing. They decrease blood pressure by increasing sodium secretion by the kidneys. They increase glycogen synthesis and glucose oxidation in the muscle. So that means that you'll store more glucose from your diet and oxidize more of the glucose. In adipose tissue, this is where the weight loss occurs. You see increased lipolysis. This is increased breakdown of fatty acids, increased free fatty acid synthesis, so that's breakdown of fats into free fatty acids, and increased glucose uptake, so the fatty tissues are starting to use more energy. There's decreased hepatic glucose production because GLP-1 antagonizes glucagon activity, so you don't produce glucose from amino acids in your liver. And then your pancreas is signaled to increase insulin secretion, decrease glucagon signaling. That's what we talked about on the previous slide. Increase insulin biosynthesis, and it enhances the function of beta islet cells. These are the cells that produce insulin. It also increases gastric emptying times, which can be uncomfortable for some people. It increases acid secretion and decreases gut motility, which can slow down the gut sufficiently to cause constipation and so forth. So, those are some of the actions of GLP-1, and this pharmaceutical comes with some risks of serious side effects. So that's where I will have you working in class to work in groups of two or three to discuss GLP-1 agonists, their role in weight loss, their effects on blood pressure, digestion, blood fats, blood glucose, how the side effects of GLP-1 agonists decrease appetite, increase nausea for many people, and decrease nutrient intake to the point where it can become dangerous. And then there are, of course, these side effects that are associated with some of these hormonal effects on the body. Um, this will be done in class, and I'll be grading your responses.